one of the present most unmistakable and high-level physicists, has offered his viewpoint with regards to this issue. Kaku, perceived for his extraordinary commitment to the fields of physical science, has as of late affirmed that the James Webb Space Telescope has found 6 enormous systems that researchers thought couldn't exist. These examinations can possibly open up new aspects in our logical comprehension of the universe. The disclosure is both energizing and progressive, testing existing speculations about the arrangement and improvement of worlds. It is thusly worth watching out for these improvements. The affirmation by such a recognized researcher as Michio Kaku highlights the significance of these discoveries. Michio Kaku is an extraordinary figure in the logical field, a physicist of American and Japanese legacy. He is viewed as a specialist in both old-style exploratory physical science and quantum mechanics. Dissimilar to a few additional moderate and suspicious researchers, Kaku doesn't have a place with that gathering and has been open to the astounding consequences of the James Webb Space Telescope mission. His eagerness to embrace new revelations and offer them with the public highlights his obligation to propelling our comprehension of the universe. We are glad that this recognized researcher has chosen to end his quietness and freely share what can no longer be denied. The excitement and almost entertained tone of the prestigious heavenly physicist are obvious in his remarks on the discoveries made by the James Webb Space Telescope. He expressed that this has been a highlight that has provoked his curiosity. Join us to discover the ramifications of Michio Kaku's disclosure of these 6 massive systems. Kaku is a researcher who has forever been willing to consider new hypotheses. Throughout his life, he has demonstrated openness to ideas that challenge the status quo, understanding that Einstein's conditions of relativity and Newton's regulations, while primary, are insufficient to capture the full intricacy of the universe. Kaku comprehends that the discoveries of the new telescope can potentially enhance the scientific field. Although many of his colleagues have not adopted this view, it is creating concern and sleeplessness among proponents of the Big Bang and opponents of quantum mechanics. However, this only provokes laughter from Kaku. The JWST has revealed the discovery of 6 gigantic galaxies tracing back to the earliest eras of the universe. Each of these systems contains more stars than our own Milky Way, despite having formed just a short time after the Big Bang. The team of astronomers who made the discovery has named these rare universes galaxy breakers, as, if confirmed, they would revolutionize our entire understanding of the universe. The implications of these findings are significant, suggesting that the universe's early years were far more dynamic and complex than previously thought. Something doesn't fit here anymore. The Big Bang theory tells us that the universe was chaotic after the initial event. The first solid objects needed millions of years to form, and it took millions of additional years for these objects to reach sufficient density and produce light. The formation of complex structures, such as galaxies, was believed to happen much later. Some of the newfound systems exceed the Milky Way in size, and their immense luminosity indicates that they were likely forming many new stars each year, while our galaxy forms stars only occasionally. It remains unclear exactly when the first galaxies formed. Scientists have not been able to determine this definitively. What is clear is that, at first, there may have only been single stars or groups of stars, which eventually combined to form increasingly larger conglomerates until dwarf galaxies developed. The small galaxies encountered other galaxies and gradually grew. By past theories, highly organized and massive galaxies could not have existed at that time, which raises the question of whether the universe is much older than previously believed or whether complex galactic arrangements developed much sooner. This scenario is hard to accept for conservative science, which still finds issues with this model. Some aspects of physics heavily decline to accept this revelation and question potential errors in the age estimations. Kaku is aware of this and had this to say. There are many instances of old and false theories that persist stubbornly due to the esteem of certain scientists. Many of these theories were only discredited when an essential experiment revealed their falsehood. Thus, the fundamental work in any science, especially in physics, rests with the experimentalists who keep the theorists alert and aware. On Earth, we know very little about the true origins of the universe. This statement from Kaku underscores the importance of continuous experimentation and validation in the scientific process. The Big Bang Theory was established in 1927 based on observations of the expansion of the universe. These data led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to consider a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in reality was beyond people's imagination. Even today, scientists still face difficulties in grasping this concept. However, it is crucial to consider these probabilities. These new findings do not fit at all with what researchers have based their understanding of the Big Bang Theory on for decades. However, science has shown time and again that reevaluation and openness to new ideas are an essential part of the scientific process, just as the confirmation of certain theories and observations was in the past. When Einstein was a child, it was believed that the stars and planets were firmly fixed in the universe, and these specific structures occupied a defined space. However, we now know that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at many kilometers per second, and entire galaxies move rapidly through the universe, the fate of which we cannot yet predict. This dynamic understanding of the universe challenges long-held beliefs and highlights the need for ongoing inquiry and adaptation in scientific thought. Today, scientists are challenged to accept uncomfortable truths and to understand that theories are not absolute truths until they are rigorously tested or confirmed by empirical observation. The idea of the Big Bang arose from the recognition that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a long time, elements such as cosmic background radiation, the redshift of light from distant galaxies, and other cosmological structures appeared to support this theory. However, it is essential to remember that in the past, people who believed the Earth was flat and that the Sun revolved around it also had physical evidence for their assumptions, until events or technological advancements provided a clearer and more accurate picture. Currently, we are witnessing a similar situation. Scientists expected the new James Webb Space Telescope to confirm assumptions related to the Big Bang, but instead, they have discovered these 6 galaxies that seemed impossible. Eyewitnesses move comparatively with one another. To comprehend this, you can envision stopping and seeing a vehicle coming towards you. As the vehicle moves towards you, you hear the motor getting stronger. However, once the vehicle passes you or creates some distance from you, the motor changes. This is because the sound of the motor varies as the vehicle moves. The same is true for light. When a light source, such as a distant star, moves towards us, the light we see shifts towards bluer tints. On the other hand, when the light source creates some distance from us, the light moves towards redder shades. This phenomenon is called redshift. Physicists have converted redshift values into speeds and distances for estimation in the study of the universe. However, it is vital to note that small errors in these estimations could have significant impacts. The estimation methods previously used are currently under review, and it will be interesting to see what results scientists arrive at regarding the latest demonstrations related to our universe. It is important to consider whether these results are truly based on redshift errors or whether some scientists are simply denying the facts. This is a question that requires rigorous investigation and careful review of the data and techniques used in the analysis. The current investigation and reassessment of estimation methods highlight the evolving nature of scientific inquiry. Many thanks for watching the video. As always, we remind you that you can post your questions in the comments box. If you liked the video, don't forget to hit the like button, share it so it reaches more people, and subscribe to the channel so you don't miss more content like this. Thanks again for watching and see you in the next one. This call to action encourages viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific discoveries. The study of our universe, with its vast scales and complex celestial structures, continues to captivate and challenge scientists across the globe. From the early theories of the universe to the latest discoveries made possible by cutting-edge technology, each discovery reshapes our understanding of the cosmos and pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are cosmic cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is crucial not only for unraveling the mysteries of our universe but also for confirming or challenging existing theories, such as the Big Bang Theory. The Big Bang Theory, proposed nearly a century ago, suggests that the universe began from a singular, infinitely dense point and has been expanding ever since. This idea emerged from observations of the universe's expansion and the cosmic microwave background, CMB radiation, considered the remnants of the early universe's intense heat and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang Theory. The JWST, with its exceptional sensitivity and resolution, has identified galaxies that defy conventional understanding. These galaxies, dating back to within a few 100 million years of the Big Bang, are unexpectedly massive and luminous, suggesting a more dynamic early universe than previously imagined. The implications of these findings are profound. They raise questions about the timeline and mechanisms of galaxy formation, forcing scientists to reconsider existing models. For example, the discovery of galaxies that are already so developed shortly after the Big Bang challenges the idea that galaxy formation was a slow and gradual process occurring over billions of years. Moreover, the JWST observations have highlighted the complexity of cosmic evolution. It is now clear that galaxies can grow rapidly and have significant star formation activities early in their histories. These insights motivate astrophysicists to revise their theories on how stars, gas, and dark matter interacted in the universe's infancy to form the first galaxies. Beyond reshaping our understanding of galaxies, these discoveries underscore the critical role of technological advancements in pushing the frontiers of astrophysical research. The JWST, with its infrared capabilities, allows scientists to peer further into space and back in time than ever before. By studying the light emitted by distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that prevailed during the universe's early stages. The concept of redshift, a crucial tool in cosmological research, plays a vital role in these studies. Redshift refers to the phenomenon where light from distant celestial objects shifts toward longer wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable information about an object's distance and velocity relative to Earth. Through meticulous analysis of redshift data, scientists can deduce the size, age, and evolutionary stage of galaxies observed by telescopes like the JWST. However, interpreting redshift measurements requires precise calibration and an understanding of potential sources of error, such as gravitational lensing and instrumental limitations. In addition to studying individual galaxies, astronomers are also exploring larger cosmic structures, such as galaxy clusters and superclusters. These vast assemblies of galaxies, bound together by gravity, offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement of galaxies and measuring their velocities, researchers can trace the cosmic web, a filamentary structure that spans across the universe and defines the large-scale architecture of the cosmos. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang itself. As the universe expanded and cooled, the intense heat of the early universe diminished to a few degrees above absolute zero, leaving behind this pervasive background radiation. Detailed measurements of the CMB's temperature fluctuations provide a snapshot of the universe's infancy, revealing primordial density variations that eventually gave rise to the galaxies and cosmic structures observed today. Satellite missions, such as the Planck Observatory, have mapped the CMB with unprecedented precision, confirming key predictions of the Big Bang Theory while also revealing anomalies that challenge current cosmological paradigms. One such anomaly is the presence of cold spots and unusually large voids in the CMB maps, suggesting unexpected patterns in the early universe's density distribution. These anomalies have sparked debates among cosmologists, prompting alternative theories such as inflationary cosmology, a concept proposing that the universe underwent a brief period of exponential expansion in its earliest moments. The quest to understand the origin of cosmic structures extends beyond traditional astrophysical methods. Particle physics, particularly experiments conducted at high-energy colliders like the Large Hadron Collider (LHC), seeks to replicate the extreme conditions of the early universe to test fundamental particles and forces. Additionally, the search for dark matter and dark energy continues to fascinate cosmologists. Dark matter, hypothesized to comprise about 27% of the universe's total mass-energy content, exerts a gravitational influence on galaxies and other cosmic structures despite emitting no detectable electromagnetic radiation. Its elusive nature has spurred numerous observational and theoretical efforts to identify its constituent particles and understand its role in cosmic dynamics. Similarly, dark energy, accounting for approximately 68% of the universe's energy density, drives the accelerated expansion of the universe observed in recent decades. Its origin and properties remain enigmatic, posing profound questions about the ultimate fate of the universe and the nature of fundamental forces governing cosmic evolution. The pursuit of these fundamental questions requires interdisciplinary collaboration and the integration of observational, theoretical, and experimental approaches. Astronomers, astrophysicists, cosmologists, and particle physicists work together to decode the cosmic narrative written in the light and structure of the universe. In sum, our exploration of the universe is a journey of discovery and redefinition, a testament to human curiosity and ingenuity. From the early pioneers of cosmology to modern astronomers peering through the lenses of space telescopes, each generation adds new chapters to our cosmic story. As we continue to unravel the mysteries of galaxies, dark matter, and the cosmic microwave background, we inch closer to understanding our place in the vast expanse of space and time.